One of the things that we should make explicit is that if this combination of Vj and Wk is a basis for our tensor product Hilbert space, H1 cross H2, then in fact we also said something about the inner product there. Because if this is a complete orthonormal basis, and this is a complete orthonormal basis, and this is a complete orthonormal basis, then the inner product between this basis state and the other basis state is going to be the delta function. And of course it has to be the delta function in both indices. And this is particularly unsurprising because there aren't very many ways you can make an inner product out of two Hilbert spaces. So we have an inner product between items in Hilbert space 1, and we have an inner product between items in Hilbert space 2. So if I'm trying to take an inner product between two things like this, then in some sense all I can really use is some relationship between the bracket inner product for Hilbert space 1 and the bracket inner product for Hilbert space 2. And the obvious thing to do is in fact just to multiply them. So what we have here, you can see if I was to think about it that way, I would have the delta function from the inner product in Hilbert space 1, and I'd have the delta function from the inner product in Hilbert space 2, just multiplied together. And indeed, that's how inner products work. So if you expand out what this implies, if you ever have two items like this, we have a generic thing, tensor product with a generic thing, and you want to take the inner product with something else, you just do the normal inner product for the first Hilbert space and the normal inner product for the second Hilbert space, and multiply them together. Now when you have entanglement and you have tensor products between two correlated objects, you also get rather strange effects from measurement, or at least they seem strange if you really deeply believe in relativity. Now the classic example of this came from the famous thought experiment by Einstein, Podolsky and Rosen, who suggested we consider two particles that start nearly at rest but explode away from each other. And if they explode away from each other, then of course momentum is conserved, and so they'll have roughly equal and opposite momentum and roughly equal and opposite position. But they won't have precise momentum and position, so they'll have some spread in each. So there we have a kind of spatial axis, and if we draw the wave functions of the two particles, then they're equal and opposite position, more or less, and also they'll have roughly equal and opposite momenta. Now I've drawn these green arrows to kind of indicate that there's a spread of momenta, and there's our envelope in our position, but we also have some kind of phase winding on those things. Now the interesting thing, of course, is that although we have this spread here is not completely supposed to be independent from this spread, because a particular momentum here is supposed to be correlated with a particular momentum over here. So we have very much an entangled state here. Now what happens if we measure just one side? So if we measure just the left side, and suppose we measure velocity or momentum, what we should get is this side collapsing to a particular momentum eigenstate. Now if that happens like this, in other words, we have just one momentum eigenstate over here, or something very close to it, and this one hasn't changed, then what we've done is we've broken the correlation between these two things, because if we measure the momentum over here, what we're saying is that we might not get the equal and opposite momentum as on the left. So if we have wave function collapse happening over here for this particle that doesn't change this one, we actually entirely lose the possibility for correlation. So in fact, the only way that correlation can be preserved is if the wave function collapse happens for the entire entangled state at once. And when you measure the momentum over here and that collapses, the momentum that's entangled with it collapses as well. And so we have a momentum eigenstate on both sides. And similarly, if we were to measure position on this side, this would collapse to some position within this envelope, and this one over the other side would collapse to the equal and opposite position within that envelope. And that looks like a very non-local thing, and indeed it is. Wave function collapse was always non-local. This is highlighting it particularly. If we measure a particle, then a distant, possibly causally distant particle will collapse at the same time. So entanglement, this Hilbert space doesn't know anything about the fact that we want things to happen locally, and wave function collapse happens for the entire Hilbert space at once. For Einstein, as he expressed in the original EPR paper, this led to a feeling that quantum mechanics itself wasn't complete, that it wasn't giving us all the information, because he strongly felt that there should be a strong causal relationship between things that happen. And of course, relativity tells us that that means that things have to happen locally and changes have to propagate locally. And so a non-local wave function collapse to him was actually a sign of ignorance. It was a sign that our information about what was going on was changing non-locally, but the actual real effects were happening locally. And so there was a deeper theory, deeper than quantum mechanics, that should tell us what was really going on.